Hello, my dear students. Please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
Okay, student. Now we'll see baseband data transmission. Okay. Now, what is a baseband? Now, any signal which is having a significant low frequency component is called as a baseband signal. Okay. A signal which is having a significant low frequency is called as a baseband signal. Okay. So, this is a baseband signal transmission. Baseband signal data transmission is nothing but, now you know that our original signal, which is a message signal, which is a continuous wave signal, continues in amplitude, continues in time. Is it right or not? Continues in amplitude and continues in time. Now you already start the digital communication, and the first block of a digital communication system which is already completed, sampler. Okay, sampling, right? Now what is the sampling? Now continuous in amplitude and a continuous time signal will be converted to discretizing in time. Discontinuous in time is called as sampling. Discretizing in time is called as sampling. Now a continuous time signal will be converted to a discontinuous in time is called as a sampling. Okay, and what type of sampling is good? Now generally what are the different types of sampling? Oversampling, undersampling and ideal sampling. Okay, so we always go for a oversampling, now which is good, and successful reconstruction is possible. All these things you already covered. Okay, never do the undersampling because the aliasing effect will be taking place, and a minimum sampling is called as a Nyquist rate, or that is also called as ideal sampling. Okay, anyway, we'll do the signal with a best sampling rate is nothing but a oversampling rate. A oversampling rate is nothing but signal is sampling rate which is greater than the Nyquist rate. This is nothing but a oversampling. Okay, now this part you completed. Okay, only sampling part you are completed. Okay, now after that sampling, now that sampled signals will be going to the quantization process. Now that quantized samples, okay, now that quantized samples is going the process of encoding. Then the output of the encoder is a sequence of ones and zeros. The output of the encoder is a sequence of ones and zeros. Now this is the binary data. Sampling, quantization, encoding process is required to convert a continuous wave signal into a binary data, digital data. Then that signal is passing through the channel. That signal is passing through the channel. But because of the various losses associated in the channel, definitely the signal strength gets decreased. Okay, affected by noise. So that noise affected binary data strength, that noise affected binary data is applied to a regenerative repeater. The regenerative repeater will eliminate that noise. Now I can write like this. Overview I am giving, but individual also I am saying. This is binary data. But when it is entering into the channel, binary data plus noise. This regenerative repeater, I just give overview, and after that I will start individual blocks one by one. Okay, not a problem. So this regenerative repeater eliminate this noise and regenerate the actual binary data. Okay, but now what is the decoder? Now the decoder output, again these binaries are converted to samples. Okay, so this binary data is converted to samples. Now here the original signal is converted to samples, then quantized samples and ones and zeros. Now in the reverse way, these are the binary data. Now decoder will be the quantized samples, reverse. Receiver operation is nothing but reverse. Now this quantized samples will be converted to a continuous wave signal with the help of low pass filter. That process which we already completed in the sampling theorem, first block of the digital communication system. Okay, so this is I hope you understand, this portion is nothing but transmitter, transmitter output is ones and zeros, and this is passing through the channel, and again finally now this part is nothing but receive. Okay, clear or not? Now this is a transmitter and receiver. Now this is called as, actually this block diagram is nothing but pulse code modulation technique. This is PCM transmitter portion, this is PCM receiver portion. Okay, don't confuse. Sampling, quantization, encoding is PCM transmitter. Okay, pulse code modulation transmitter. Now decoder, low pass filter is a PCM receiver. Now in addition, in between the transmitter and receiver there is a channel, there we are using the regenerative repeaters. Okay, so all these particular block diagram we are perfect, and we are get a very clarity about the sampling. This much is we are good. We don't know what is quantizer, encoder, all these things I don't know. We know only this sampling. Okay, what is a sampling, what type of samplings are available, what the sampling theorem says. Now in digital communication, now which type of sampling which you are followed. This much is we already have aware of that, because we have completed the first part of the digital communication system is nothing but a sampling. First topic is a sampling theorem. Okay. So now after that everything is new to you. Quantizer, encoder, regenerative repeater, decoder, all these things we don't know. Okay. So this is a block diagram of PCM. First you know down, and after that I will take a individual one by one I am taking. Okay, one by one I will dictate. You know down. Clear or not? Okay. Now see here. Now we'll finish one by one block. Now I want to first finish the PCM transmitter portion. Okay. Now what is PCM transmitter? Now this is a PCM transmitter. Now this you know that continuous and amplitude, continuous time signal will be converted to continuous in amplitude and continuous time signal will be converted to discretizing in time, this is at TS seconds, 2 TS seconds, 3 TS seconds, and let us take this is from 4 TS seconds. Now this is the discretizing in time, discontinuous in time, and these amplitudes will be same as of the message signal amplitudes. I just use a continuous amplitude word. So this is a continuous wave signal, analog signal. This is a sampled signal. Up to this portion we are clear. Sampled signal. Now this sampled signal is undergoes the process of quantization. What is quantization? What is quantizer? What it will do? We want to identify first. See here, the quantizer which is used in the transmitter to round off the sample values to the nearest quantization level. Okay, what is the meaning of that? Quantizer, let us take here this is 0.9, here 1.8, here 3.6, and this is 5.8, like this for example. Now what is the job of the quantizer? At TS 0.9, at 2 TS 1.8, at 3 TS 3.6, at 4 TS 5.8, original sample values. Okay. Now this quantizer is round off these sample values to the nearest quantization level. Let us take 0.9 is round off to 1, 1.8 round off to 2, 3.6 round off to 4, 5.8 round off to 6, like this. Okay. Sir, how it will be round offing? 0.9 is nearest to 1 or that we will see. Okay, this is general. Okay, the quantizer is used in the PCM transmitter to round off the original sample values to the nearest quantization level. Okay, note down or not? Quantizer is used in the PCM transmitter to round off the original sample values to the nearest quantization levels. Okay, here one word is coming, quantization level. Okay, round off to quantization levels. What is quantization levels? How many quantization levels is a question mark. Second one. Okay, clear or not? Okay, now these are the sample values, or we call it as I am using the word original sample values, means this sample amplitude, message signal amplitude at TS seconds will be same, exactly same. These are the original sample values. Original sample values. Okay. To identify the number of quantization levels, now we also require signal strength boundaries. Signal strength amplitudes. What is this? Signal strength amplitudes. Now first we will require what type of signal which we are transmitting, what is the peak amplitude, what is the minimum amplitude, what is the frequency. Okay, this is the signal strength amplitudes we require to designing a quantizer. Okay, what is the signal strength amplitudes? Is nothing but maximum amplitude and minimum amplitude. Okay, signal strength amplitude means what is the maximum amplitude of the signal, V maximum, and what is the minimum amplitude of the signal, we required that. Okay, and now this is the quantization levels, this is the maximum and minimum. Okay, this much information first we required to design anything. Okay, so what type of information which you are transmitting and how the quantizer is working. Okay, so now see here, now we'll stop here and now we'll start designing a quantizer. Okay, now I just put heading here, then you understand or not? How many quantization levels and what are the number of quantization levels, I don't know. but quantizer job is round offing. Okay. Now to know identifying here, I required the signal strength. What should be the signal strength, right? What is the maximum amplitude? What is the minimum amplitude? What is the next block? The next block is nothing but encoder. Am I right or not? Actually, this encoder is nothing but, practically the encoder is nothing but n bit A to D converter. Practically this encoder is nothing but n bit A to D converter. What is the meaning of that? N bit A to D converter, which means that, let us take for example, okay, now you just here. This is one sample now. At TS seconds, this is one sample. Now this sample strength is converted into how many bits? Let us take for example, this is 2-bit A to D converter. This is 2-bit A to D converter, means each sample is encoded into 2 bits, whether it is 10 or 01 or 00 or 11, whatever it means, right? Now this is a 2-bit A to D converter. No sir. Now this is 3 bits, sir. This is a 3-bit A to D converter, which means that each sample is encoded into 3 bits. If it is a 4-bit A to D converter, which means that each sample is encoded into 4 bits. Okay, not 1010, 4 bits, right? Not 1000, 3 bits, not 10, it is 2 bits. Okay, now this is the encoder job. You purchase what type of encoder you can require, you can take a encoder and connect it here. Then the encoder job is whatever the sample is coming, whatever the input is coming to the encoder, now that sample value is directly converted to the binary sequence of ones and zeros. Whatever the quantized samples, all that quantized sample values are converted to ones and zeros. Clear or not? Now this is the encoder output and this is the job of the encoder. Therefore, now you want another information you required. What type of which bit A to D converter required to transmit the information? Means what? What is the meaning of that? Which bit A to D converter required to transmit the information? Let us take for example, this strength is 1. This sample strength is 1. So the signal strength 1 volt can be accommodated in 2 bits. 100% correct. This is correct. We can accommodate it in 2 bits, not a problem. Is correct. Means 2 bit is sufficient. This is correct. Now this is the signal strength. Now this is the signal strength of 4 volts. Now the signal strength of 4 volts can be accommodated in 3 bits. Yes. So this is correct. This is also correct. Now the signals, this is a 3 bit. If one of the sample strength is 10, so the signal strength 10, can I accommodate it in a 3-bit A to D converter? No. For representing a signal strength 10, how many minimum bits we required? We required minimum 4 bits. But how much you are taking? 3 bits. So you are converting into 3 bits is not possible, right? Now this is wrong. Now 3 bits are not whole, not represent a strength of 10 volts. Clear or not? Sir, how I can know that this is 1 or 4 or 10? You only know that what is the input to the PCM is a message signal. You know the message signal strength. You know what is the signal strength, what is the signal amplitude. You know maximum, you know minimum. You can easily decide. Now take the maximum value. Don't take a minimum value. Take the maximum value. Let us take maximum value is 10 volts. So you can take a minimum 4-bit A to D converter. A maximum value is 15. Okay, if maximum value is 15, you can take accommodate in 4-bit. Maximum value is 17. Maximum signal strength is 17. 4-bit A to D converter is not sufficient. Then go for 5-bit A to D converter. Okay, sir, maximum value is 7. Yes, 3-bit A to D converter is 7. Sir, maximum value is 8. Yes, 4-bit A to D converter required. Maximum value is 7. 3-bit A to D converter is sufficient. Maximum value is 100. No, 2-bit, 3-bit, 4-bit are not sufficient. Okay, take a 7-bit A to D converter. Okay, like this. Clear or not? So these steps means which bit A to D converter you already decided based on the information. Which bit A to D converter required to transmit the information can be decided based on the message signal strength. Clear or not? This information required information. This information is required to design a quantizer. Okay, and best quantizer also. Okay, so now you know this information. Yes, sir, we have this information. And based on this information, you know which type of A to D converter is sufficient to carry this information? Yes, sir. So then how many number of quantization level? You don't know. How many are the quantization levels you should take? You don't know. If you know these two, automatically you can get that. Not a problem. Okay. Now we'll do that. Okay. Now first you take this, then I will take one by one and designing of n bit converters. Okay. And one more thing, one more point I missed here. Now here each sample is encoded into 2 bits. If your encoder is a 2-bit A to D converter, this is named as 2-bit PCM system. This is also named as 2-bit PCM. If anybody is saying that I am designing a 2-bit PCM, what is the point in your mind? Oh, 2-bit PCM system means encoder is 2-bit A to D converter. 2-bit PCM system means encoder is a 2-bit A to D converter. Now, this is the 3-bit PCM system, 3-bit A to D converter. 3-bit A to D converter, which means that 3-bit PCM system means encoder is 3-bit A to D converter. Each sample is encoded into 3 bits. That is the meaning of that. Clear or not? 4-bit PCM system means each sample is encoded into 4 bits. That is the meaning of 2-bit PCM system, 3-bit PCM system, 4-bit PCM system. Therefore, which bit A to D converter required to transmit the information can be decided based on the message signal strength. Means we know that which type of PCM system, am I not? Means we know that which type of PCM system we are designing. Clear or not? These points are clear or not? So whether you want to design a 3-bit or 4-bit or 5-bit, you know earlier. Without doing quantizer also you know. Now forget about a quantizer, but you know the PCM, which type of PCM, because the which type of PCM system which we are decided based on the message signal strength. Okay, note on this. Okay, now we'll start designing of the quantizer. Okay, so now here I write design steps to designing of n bit PCM. Okay, designing of n bit PCM system. Now I'll write the steps here. Now what is n? Where n is nothing but, what is n? N equal to number of I'm already explaining 2-bit PCM, number of bits per sample. Number of bits per sample, n is. Okay, then I will take one small problem. Now see here, this is a signal strength. This is a signal whose amplitudes are varies from 0 to 8 volts. Okay, this is a signal whose peak amplitude is varies from, this is a signal whose peak amplitude is varies from 0 to 8 volts. Now this is a signal strength whose amplitudes are varies from 0 to 8 volts. Then this signal, this continuous wave signal is undergoes for the sampling. Now this continuous wave signal will be discontinuous in time, discretizing in time. Now what are this discretizing in time amplitudes is? Now this is at TS seconds, at 2 TS seconds, at 3 TS seconds, at 4 TS seconds. Let us take for example. Okay, now this is for identifying this sample values, then I take the amplitude scale. Okay, now this is 2 volts, 4 volts, 6 volts and 8 volts. Okay, this is the signal strength. Signal scale, this is the original information, signal amplitude. Now this signal amplitudes, now these are the signals, I will write the values here. This is 0.9. Now this is 2.2 something. Now this is 4.3. Now this is 6 and 8. This is some 7.5 something. Okay. Now these are the original sample values. Okay. At TS seconds, at 2 TS, at 3 TS, at 4 TS. Okay. These are the samples values. Okay. Now these original sample values undergoes the process of quantization. Now I want the quantizer designing process. Now I want the quantizer designing process. Now first we want what type of information, which bit PCM system I know. Okay. Now let us take for example. Okay. For example, for easy calculations purpose. Okay. Don't take exactly 2. Okay. You 3 or 4, that depends upon the signal strength. Okay. Now for example, this is a 2-bit A to D converter. Let us assume this is 2-bit A to D converter. Okay. So what is n value? N value equal to 2 here. Okay. In this example, n value equal to 2 for example. Now this n equal to 2-bit PCM system. Okay. Now, so now I am designing a 2-bit PCM system. Now first step is, what is the signal information? Step 1 is called as dynamic range. Now what is the dynamic range? The dynamic range, which is nothing but maximum voltage minus minimum voltage. The dynamic range is nothing but V maximum minus V minimum, which is nothing but, now see here, what is the quantizer maximum possibility? 8. What is the quantizer minimum possibility? 0. Which means that V maximum minus V minimum, which is also called as maximum possible input to the quantizer, maximum possible input to the quantizer minus minimum possible input to the quantizer. Maximum possible input to the quantizer minus minimum possible input to the quantizer. Now this is called as the dynamic range, and this V maximum, V minimum, which is also called as V peak to peak or V peak to peak, this is the dynamic range. Okay, the maximum possible minus minimum possible, maximum possible input to the quantizer, minimum possible input to the quantizer, or V peak to peak is the dynamic range. Okay, now in this example, now take this example. In this example, n value is 2. Now in this example, the dynamic range is V maximum minus V minimum, 8 minus 0, which is equal to 8. Okay, now second step. Total number of quantization levels. The total number of quantization levels, we require the number of quantization levels. Okay, the number of quantization levels represented by capital L. The number of quantization levels is always a power of 2 power n. So the number of quantization levels L, which is equal to 2 power n. Okay, because you know this sample value is round off to the nearest quantization level. What is the quantization level? How many are there? So the total number of quantization levels are 2 power n here. In this example, L equal to, L equal to 2 power n, which is equal to 2 power n is 2, which is equal to 4. Now you know the number of quantization levels. So in this problem, how many quantization levels? 4 quantization levels. Okay, so each sample value, each original sample value is round off to the nearest quantization levels. Okay, and students, you first think that, and most of the students are having a mistake, that quantization level is nothing but quantized sample value only. I will write that one also. Quantization level, output of quantizer is nothing but quantized sample value. Quantized sample value is nothing but 100% quantization level. Both are same. Quantized sample value or quantization levels, both are same. Okay, don't confuse. Okay, so the original sample value to the nearest quantization level, the nearest quantization level is nothing but the quantized sample value. Okay, output of quantizer. Right. Now total how many quantization levels? There are 4 quantization levels, but where should I start those 4 quantization levels? Well, whether I should start at 2 or 4 or 6 or 8, where should I start at? So we want a reference for that. Okay, so the reference is nothing but successive difference between the quantization levels the successive difference between the quantization levels is called as the successive difference between the quantization levels is called as step size. The successive difference between the quantization levels is called as step size delta. The step size, the successive difference between the quantization levels is called as step size delta, which is nothing but dynamic range by L. The successive difference between the quantization levels is called as step size delta, which is nothing but dynamic range by L. Now, what is the dynamic range? The dynamic range is 8 in this example. In this example, the successive difference between the quantization levels is dynamic range by L. Dynamic range is 8, L is 4, which is equal to 2 volts. Step size is 2 volts. Now the step size is 2 volts. So the successive difference between each quantization levels is nothing but, now one level to another level should be maintained step size of 2 volts. Okay. So now let us take here. Then I will take the first quantization level. Now the first quantization level is 1 volt. Now what should be the next quantization level? The step size should be maintained as 2 volts. Therefore, this is the second quantization level. This is the third quantization level. This is the fourth quantization level. The successive difference between the quantization level 1 volt, 3 volt. Now this is the successive difference between the quantization level is called as step size. The successive difference between the quantization levels is called as step size. Now what is the step size here? Here is 2 volts. Here is 2 volts. Here is 2 volts. Now see the students. Now here the step size is fixed or not? The step size is fixed between the quantization levels. If the step size is fixed, here I will write. If the step size, or I can write here itself. Okay. If the step size is fixed, that quantization process is called as, if the step size is fixed, that quantization process is called as uniform quantization. If the step size is fixed, that quantization process is called as uniform quantization. Okay, uniform quantizer. Which type of quantizer we are designing? A uniform quantizer. Okay, note down this. Okay. Now you know the number of quantization levels, right? Then the students are asking that, sir, why you should start here? Why you are not started 0? Or why you are not started 0.5? Why you are not started at 1.5? Is it out or not? Why you started at 1 only? That also I will tell you. Now this is the quantization level. These are the quantization levels. Okay, 1, 2, 3, 4 quantization levels. Okay. Now this original sample value. Now see here, a TS. At TS, what is the original sample value? 0.9. Now this sample value is round off to the nearest quantization level. What is the nearest quantization level? Any original sample between 0 to 2, greater than 0, less than 2 will be round off to this. Greater than 2, less than 4 will be round off to this. Greater than 4, less than 6, round off to this. Greater than 6, less than 8, round off to this. Okay. So this 0.9 is round off to the nearest quantization level 1. Next 2.2, whose nearest quantization level 2.2, whose nearest quantization level is 3 volts. Now at 3 ts seconds, now 4.3, whose nearest quantization level is 5. Now 4 ts seconds. At 4 ts seconds, 7.5, whose nearest quantization level is 7. Okay. Now these are the original sample values: 0.9, 2.2, 4.3, 7.5 is round off to the nearest quantization level. What is a quantizer? The quantizer is used in the transmitter to round off the original sample values to the nearest quantization level. These are the nearest quantization level it is round off. Okay. Now you see here, I will take a table here. At ts seconds, at 2 ts, at 3 ts, at 4 ts. Original sample values are 0.9, 2.2, 4.3, 7.5. Quantized sample value, quantization level or quantized sample value, both are same. I will mention. Okay. Now the quantized sample values are 1, 3, 5, 7, because the quantization process itself is nothing but a round off process. Okay, the quantization process itself is nothing but a round off process. So round off means we are introducing some error. Am I not? We are introducing round off. A 0.9 is round off to 1. We are adding some error. So that error is coming because of the quantization process. Therefore, that error is called as quantization error. Definitely it will come. Okay. Now what is the next one? Fourth one is quantize. Step 4 is quantization error. What is the quantization error? The quantization error, which is nothing but quantized sample value minus original sample value. Error means deviation, whatever it may be, or original sample value minus quantized sample value. Quantization error is nothing but a deviation. So error means plus or minus, whatever it may be. Quantized sample value minus original sample value, or original sample value minus quantized sample value. Okay. So the quantized sample value, which we call a quantized sample value, which is equal to original sample value with some quantization error. Is it or not? See here, the quantized sample value, which is nothing but original sample value with some quantization error. So this quantization error should be as minimum as possible, such that your quantized sample value is very close to the original sample value, because you are introducing some error, you are adding some error. Therefore, this quantization error should be as minimum as possible. Am I not? So, therefore, the quantization error should be as minimum as possible. And what should be the boundaries of quantization error, and how much quantization error should be accepted? How much quantization error should be accepted value is how much error is acceptable. Okay, so that also we have to be identified. So this quantization error, see here, the quantization error is always, that is the successive difference between the levels. Therefore step size, it depends upon the step size. Therefore the quantization error acceptable value is minus delta by 2 to plus delta by 2. Now from here, the maximum allowable quantization error is plus delta by 2. So in our example, in our case, what is the step size delta? Delta is 2. So therefore, minus 2 by 2 minus 1 volt less than quantization error less than plus 1 volt. And what is the maximum quantization error? In our case, the maximum quantization error is delta by 2, which is equal to plus 1. Now this much is acceptable. How much you are getting? Now the quantization error, which is equal to quantization error, which is nothing but quantized sample value minus original sample value. Quantized sample value minus original sample value, whatever may be, it is a deviation. Okay, not a problem, students. So 1 minus 0.9, 0.1, 3 minus 2.2, 0.8, 5 minus 4.3, 0.7, 7 minus 7.5 minus 0.5. Now all these quantization errors within this boundary or not, minus 1 to plus 1, minus 1 to plus 1, and maximum allowable quantization error is plus 1, which is not exceeding plus 1. All are less than 1, all are in between minus 1 to plus 1. Now in such a situation, whatever the quantizer you are designing is acceptable. And the students are asking a doubt that, sir, why should you start at 1? You should start the quantization level representation at 0. Not a problem. You should represent the quantization level at like this: 10, 12, 14, 16. These are also the quantization levels. How many quantization levels? 1, 2, 3, 4. 4 quantization levels. And maintain a step size of 2 volts, 2 volts, 2 volts. Fixed uniform quantization. If you design like this, what should be the what things will be taking place? So let us take first. 0.9 is round off to 10. 0.9 is round off to 10. Means what should be the error? 0.9 and this is 10. 9.1 is the error. But what is the maximum error? Only 1. But how much error you are getting? 9.1 is unacceptable. Nobody will use that type of quantizer. Error will be very, very high, and there is a large deviation between the original signal and the reconstructed signal. Okay, that's why while designing the quantization process, the quantization error should be within the acceptable limits. Okay, this is the quantization error. So once the quantization error process is completed, very simple. Now each quantization level is encoded into 2 bits. Okay, 2 bits. This is just for example. Okay, not 1 means not 0 0. For example. Okay, so now each quantization level, see here, each quantization level. Now this is the quantization level 1. Now this quantization level 1 is encoded into 2 bits. 3 is encoded into 2 bits. 5 is encoded into 2 bits. 7 is encoded into 2 bits, because this is a 2-bit PCM system. Each quantization level is encoded into 2 bits. Therefore 0 0, therefore 0 1, therefore 5 means 1. Therefore, 7 means 1, 1. Each quantization level is encoded into 2 bits. Okay. Now, this is a 2-bit PCM system. Each quantization level is encoded into 2 bits. Each quantization level is encoded into 2 bits. Each quantized sample value is encoded into 2 bits. Each quantized sample value is encoded into 2 bits. Now, this is the sample value and this is the binary data and this is the original information. The continuous wave signal will be converted to a sequence of ones and zeros. Okay. Now, this is the sampling, quantization, encoding. Okay. But now the question is, students are asking, sir, why the modulation comes into picture? Now, what is the meaning of modulation? Here, the modulation is nothing but not high frequency carrier, low frequency signal modulation. That is actual modulation, but that is analog modulation. Here is also the same modulation, but why here the word the modulation is coming? This is not the carrier type modulation. Here, the word modulation is using here. The reason behind that is each sample. See here, each sample is encoded into 2 bits. If it is a 3-bit, each sample is encoded into 3 bits. Okay. So, which means that the pulse codes, this is code 0101 pulse codes are varied. Pulse codes are varied according to the sample value. Pulse codes are varied according to the sample value. So it is called as pulse code modulation, because generally the modulation is nothing but a pulse carrier characteristic parameters are varying. Here is also the pulse codes are varied according to the sample value. That is the reason why this is called as pulse code modulation.